Hello everyone, welcome to my live video lecture. I am Dr. Namarata Gangil and I am from Akgec Engineering College, Ghaziabad. So today I will be delivering my lecture on introduction to metal forming process. So metal forming process basically a shaping process. It is basically a shaping process. So there are mainly four types of shaping operation like liquid metallurgy, powder metallurgy, machining, and forming. So in liquid metallurgy what happens, we shape the object. We initially melt the raw material and pour it into the desired cavity that we require from the final object, and after solidification we get the casting. So this happens in liquid metallurgy. In powder metallurgy we take initial raw material as a metal powder, we compact it under the die of desired shape, then after sintering we get the desired object. In machining we get the shape or size of the object by removing the material, and in forming, as it is our today's topic, we plastically deform the material to get the desired shape and size of the object. So metal forming process is basically divided into two categories based on the surface area to volume ratio. So if the surface area to volume ratio is large, then the process is called the sheet metal working, and when the surface area to volume ratio is small, then it called the bulk deformation process. So under the sheet metal working there are various processes like bending operation, shearing operations, deep or cup drawing processes. In bulk deformation, where the surface area to volume ratio is small, there are various processes like rolling, forging, extrusion, and wire or bar drawing. So all the sheet metal working processes, all the sheet metal working operations are performed at room temperature. So we say it in cold condition, whereas all the bulk deformation processes can be carried out in cold, warm and hot conditions. So sheet metal working process is performed generally at the room temperature, we call it a cold condition, and all the bulk deformation processes can be carried out in cold, warm and hot condition. So first let us understand what is cold, warm and hot forming processes. So hot working, in hot working the plastic deformation occurs above the recrystallization temperature of the material. So recrystallization is the process in which the older grains disappears and the newer grain forms, and recrystallization occur above the recrystallization temperature, and the plastic deformation in which the forming is done at above the recrystallization temperature is called the hot working process, whereas in cold working process the plastic deformation occur below the recrystallization temperature of the material. So often this range is further subdivided into hot, cold and warm working, as we can see in the figure. So hot working range is from 0.6 times the melting point of the material to 0.9 times the melting point of the material. Warm working is from 0.3 to 0.6 times the melting point of the material, and cold working range, the cold working range in which the material is plastically deformed is from the room temperature to 0.3 times the melting point of the material. So what happens during hot working? So during hot working the effect of strain hardening are negated by dynamic and static process of the recrystallization, which keep the sample or the material ductile, and the lower limit of temperature or the lower temperature is the 0.6 times the melting point of the material in the hot working process, whereas in cold working strain hardening takes place. Strain hardening is the phenomena by which the strength of the material or the hardness of the material increases due to previous plastic deformation, and the upper limit of cold working is 0.3 times the melting point of the material. So generally we say the recrystallization temperature is around 0.4 times the melting point of the material, but for pure metal recrystallizes at 0.3 times the melting point of the material, whereas impure metals recrystallizes start recrystallization from 0.5 to 0.7 times the melting point of the material, but hot working generally carried out at temperature range of 0.6 to 0.9 times the melting point of material. So what happens during cold working? So during cold working strength increases, but it is not the preferred strengthening mechanism for the applications involving high in service temperature. So the material that is used in applications where there is a severe temperature conditions, so the cold working material is not preferred in those applications. So strengthening may be called as a byproduct of shaping of the metals by the plastic deformation process of cold working, like extrusion, forging, in drawing, in all the processes in rolling, extrusion, forging and drawing. When we do the cold deformation or cold working at low temperature, strengthening always occurs. So as we know, during the cold working, the plastic deformation occur in the temperature range from 0 to 0.3 times the melting point of the material, and during cold working point defect and the dislocation defect density increases, and 1 to 15% of energy of plastic deformation stored as strain energy in these defects. So what happens during cold working? Density, point defect density increases and dislocation density increases. And during cold working, crystallographic plane fractures and which generate huge dislocations. So when dislocation in a material becomes huge, becomes large enough, dislocation density increases, so it causes the dislocation hindrance or dislocation movement. They hinder the movement of each other and strengthen the material, and common forming operations change the cross sectional area due to the plastic deformation, during the plastic deformation. So we can we can calculate the percent of cold work by taking the initial cross sectional area and cross sectional area after the deformation. So before deformation, in for any process like in forging, drawing, rolling, extrusion process are the bulk deformation process. Let us take the initial cross sectional area is AO and the final cross sectional area after the deformation process in AD in all the processes. So we can calculate the percent of cold work by this formula. Now we will see the effect of impact of cold work or percent of cold work. So in this plot we can see the stress and strain diagram and the effect of percent of cold work. So we have taken three cases here: 0% cold work, 4% cold work and 24% cold work. So yield strength in all three samples, of all three samples are denoted by blue dots. These three dots are showing the yield strength of these three samples. Red dots are showing the tensile strength of three samples and ductility is shown by the green dots. So by increasing the cold work percentage, we can see the cold working increase the yield strength of material, tensile strength of material, whereas the ductility decreases. And with increase the percentage of cold work, yield strength further increases, tensile strength increases and ductility further decreases. So here we see the difference in cold working and hot working. As we all know, in hot working, the forming process of plastic deformation is done above the recrystallization temperature of the material, and the temperature range in the hot working is from 0.6 to 0.9 times the melting point of the material. In cold working, the working is performed below the recrystallization temperature. We all know the forming operation is also called the working operations. So working above the recrystallization temperature in hot working, whereas working of plastic deformation occurs below the recrystallization temperature of the material. The second difference is in hot working is that the energy required for deformation is less due to reduced flow stress. So at higher temperature, plastic deformation is easy because of reduced flow stresses. This is the reason we can easily deform the larger products as well. In cold working, the deformation or the energy required for deformation is more because we perform the cold working at comparatively lower temperature, from room temperature to 0.3 times the melting point of the material. And in hot working, there is no strain hardening takes place in the metal because there is recrystallization after the deformation because of the higher temperature. But in cold working, there is a strain hardening takes place during the process, which increases the strength and hardness of the material. So yield strength, tensile strength increases and the ductility decreases in the cold working. When we do hot working, we cannot obtain close dimensional tolerances, whereas close dimensional tolerances can be obtained by the cold working process. Next point, the component will have the isotropic properties. Isotropic properties means when we test the material from the different direction, it will give the same material property. So where we do the hot working, we can always obtain the isotropic properties, means same properties in all direction, whereas in cold working, the component will be anisotropic in nature. So as the flow stresses are less in hot working, so large components can be easily hot worked, whereas in cold working only small components can be worked. In hot working, due to the higher temperature, there are surface oxidation occurs, scaling will be present and the surface finish is poor, and the coefficient of friction in the hot working is around 0.6, whereas the coefficient of friction in cold working processes is around 0.1. So surface oxidation and scale formation are less and surface finish is good when we do cold working. So we need extra equipment for heating of the metal in hot working operation, whereas in cold working operation we do not require extra equipment for the cold working. And when the material is hot in hot working, the handling of hot material is difficult, whereas in cold working handling is not very difficult. We can easily handle the component which we are going to form. So strain hardening is also called work hardening. So strain hardening generally occurs in cold working processes. So it is the phenomena whereby a ductile metal becomes harder and stronger when it is plastically deformed. So this mechanism can easily be seen in the stress strain diagram after the yield point and up to the ultimate tensile point. So after the yield point and before the ultimate tensile point, there is a strain hardening mechanism. We need larger force to further deform the material because of strain hardening, because strain hardening increases the strength of material when it is plastically deform. So during tensile testing, the material continuously deform plastically, and from yield point to ultimate tensile point, there is a phenomena called strain hardening can easily be seen on the stress strain diagram. So due to strain hardening, yield strength, tensile strength and hardness of the material increases with increasing the percent cold work, whereas ductility reduces. So during plastic deformation, what happens? As we know, during cold working, dislocation density increases, point defect density increases. So as the dislocation density increases, dislocation is a linear defect. So as the dislocation density increases, the average distance between the adjacent dislocation decreases, and there is a interaction between the dislocation. So when the same opposite signs of dislocation come on the same slip plane, they annihilate, whereas the same sign dislocation on a different slip plane can obstruct their movement. So there is an interaction between the dislocation and dislocation strain field. So the repulsive dislocation mobility becomes more restricted. So dislocation itself create restriction to movement of another dislocation, which causes the metal to harder and stronger. So metal by which becomes stronger and harder. So what is dislocation density and how we can measure it? So dislocation density is measured by counting the number of dislocation lines that thread in a unit area of surface, that is by per mm square, through per mm square the counting, we count the number of dislocation per unit area. We can always measure the dislocation density. It is also defined in terms of the total dislocation length per unit volume, that is by mm per mm cube. So different type of metals or different condition of metals can have different amount of dislocation density. If we talk about the carefully solidified metal crystal, it will have around 10 to the power 3 per mm cube dislocation density, whereas heavily deformed metal after the cold working can have dislocation density of around 10 to the power 9 per mm square. Heat treating a deformed metal means annealed metal will have dislocation density of around 10 to the power 5 to 10 to the power 6. So we can reduce the dislocation density after the cold working by doing the annealing process. So when we do cold working, this is the amount of dislocation density, but after the cold working, when we do the annealing, dislocation density decreases to this amount. Ceramics can have dislocation density from 10 to the power 2 per mm square to 10 to the power 4 per mm square. So now we will discuss all the forming operation, work deformation processes one by one. So rolling is the process of reducing the thickness or changing the cross section of a long workpiece by compressive forces applied through a set of rolls. So in this figure we can see there are two rollers through which a workpiece is fed. So there is a condition, entry condition for passing this workpiece material through the set of rollers. The entry condition is there are two types of forces, frictional forces and normal forces acting on the workpiece material. When the horizontal component of friction force becomes equal or greater than the normal horizontal component of normal force, then only the material starts passing through the set of rolls. So here in these two figures we can easily differentiate the cold rolling and hot rolling process. So this figure is showing the cold rolling process and this figure is showing the hot rolling process. So we can clearly see the difference in grain structure after the cold rolling and hot rolling operation. the initial grain structure is same before rolling, but what happens during rolling? During rolling, if we talk about the cold rolling operation, so you can see the grain structure is nearly equiaxed, but when it passes through the set of rollers, so what happens here? The grains deforms and becomes elongated, and after the during the deformation, when it is between the set of rollers, deformation of grain starts, grains becomes more elongated, and after the rolling operation we can get the deformed and elongated structure, grain structure in the rolling direction. Whereas in hot working, in hot rolling operation, we can see the initial grain structure is equiaxed, but during deformation grains becomes deformed and elongated, but this operation is performed at higher temperature above the recrystallization temperature of the material. So within certain duration of time and just after the rolling, the material becomes equiaxed, means recrystallization process occurs here, which replaced those grains have replaced, newer grains have replaced the older grains, and grains becomes equiaxed again. So in cold rolling we will get the deformed and elongated grains, and after the hot rolling we will get the equiaxed and recrystallized grains. So this is why there is an isotropy in the cold worked material, because the grain is not equiaxed, it is not equal, it is not of equal dimension in all the direction. This is the reason we get an isotropy in the cold work material, whereas in hot rolled material or hot work material we get the isotropic properties, because the grains becomes equiaxed and the dimension of grains is almost same in all the direction. So here in this figure we can see the rolling operation. This is the angle of contact area in which the reduction occur. So there is a two set of roller through which the hot metal is passed in hot rolling. There is a grain elongation, then further there is a grain recrystallization. So this is showing the effect on grain structure in hot rolling. So we can have common rolling arrangements like 2 high rolling mill, 3 high rolling mill, 4 high rolling mill, cluster mill, and ring rolling, depends on the kind of object we required. So in and the thickness also. So if the thickness of the material decreases, we need higher more number of rollers, more number of supporting rollers to roll the material. So hot ingot of metal is generally converted into slab, bloom, or billet. So we can see clearly, we can see the difference in the cross section of slab, bloom, and billet. So bloom and billet are generally square cross section, slab is having the rectangular cross section. So slab is used to form the plate, sheet, and strips. Bloom is the raw product for the channels, rails, and beam production, and billet is the raw material, raw product for the rod and bar production. So through continuous casting or ingots, we can have slab, billet, and bloom. So here in this figure we can see the different types of rollers, different arrangement of rollers to produce different type of cross sectional rolled products. So this is showing the schematic outline of various flat and shape rolling processes. So slab is generally used to produce hot strip, scalp, and plate through rolling operation, which further used as a raw material to produce the cold strip, pipe, and steel plates or any other plate. So hot strip is generally used to produce strip through cold rolling operation. So here on the slab hot rolling is performed, but after the reduction if we further want to reduce the thickness of the material, and if we further reduce the material and we want to obtain the strip and we want to form the strip, we can do cold working. Scalp is generally of lower width. So scalp is used to produce the welded pipe. Plate is used to further reduce the thickness of the material. We can further reduce the thickness through rolling or other operation. Billet is used as to produce hot rolled wires, and then that hot rolled wire is further used for drawing operation to produce bars and biers. Tube rounds is used to produce seamless pipe, and bloom is used as a raw material for obtaining the different structural shapes like rails and channels. So there are some some defects in the rolling operation like wavy edges, cracks and alligatoring. These are the more common defects of the rolling operations. So wavy edges, as we can see in this figure is showing the wavy edges defect. It results from concave roll bending and when the material is thinner along its edges than at its center. So this kind of defects is generally appear. Cracks may be internal crack or external or edge crack or the center crack. So cracks are generally result from the poor material ductility, convex roll bending, and severe condition causes center split. Alligatoring is the defect. It is produced when it may be produced when there is a defect in the original cast material, or when it is also produced, it can also produce when the surface of the work is only deformed. So next process is forging. So forging is the working of metal into a useful shape by hammering or by pressing. So in figure you can see a worker is blowing the hammer, repeatedly blowing the hammer on the red hot material. So this is the hand forging operation. We call it blacksmithy operation. So this is the oldest of the metal working arts. It is called the blacksmithy. We can easily see it in smithy shops. So replacement of machinery occurred during early industrial revolution. Now various kind of machines are available to produce the forged object. Forging machines are now capable of making parts ranging in size of a bolt to turbine rotor, and large ship components can also be produced by the forging process. So most forging operations are carried out in hot condition, although certain metals which are having the low strength can be cold forged. So this figure shows the open die forging. So generally the workpiece is compressed between the two die. This is the lower die, this is the upper die. So lower die is normally fixed and upper die is movable. So any workpiece or cylindrical workpiece is placed between the two dies and the pressure is applied from the upper die, then the thickness of the material, thickness of the workpiece reduces. So this figure is showing the open die forging operation. Next is impression die forging. So it is not open die forging. In impression die forging we can see there is a cavity in the die halves. This is the upper die, this is the lower die, and there is a cavity between, there is a cavity in the two die halves. In fixed die and movable die, you can see the cavity there. So this is the cavity which is required for the part, the shape of the shape or size of the part to be obtained. So in impression die forging, approximate volume of material, approximately calculated material is used and is placed between the two die halves which is having the cavity. So this is the primary cavity and there this is the secondary cavity. So some extra material during the forging operation comes into the secondary cavity as a flash in impression die forging. In this process you can see during the forging operation the material which is extra comes into the secondary cavity through moving through the land. So this space, secondary cavity, is called the gutter in which the extra material in the form of flash comes. So impression die forging cannot produce net shape. So the shape and accuracy in impression die forging is less as compared to closed die forging, and as compared to closed die forging it requires less power to forge the material. Whereas in closed die forging there is also cavity between in the two die halves, but there is only a primary cavity, there is no secondary cavity is provided. So the requirement is to use the exact volume of material. So exact volume of material is placed between the two die halves, then the pressure is applied and the forging is done. So this is the closed die forging in which no secondary cavity is provided, exact amount of material is placed between the die halves. So more power is required to for the closed die forging, and closed die forging produces the net shaped objects, and the shape and accuracy of the material, the workpiece that is obtained through the closed die forging is more as compared to impression die forging. The power requirement is large in closed die forging as compared to impression die forging, and there is no secondary cavity and minute surface details, like we can see on the coin some surface details. All the surface details are easily produced through the closed die forging. So this operation is used to produce the coins, metal coins. So these are the typical forged products. As we can see, as we have already discussed, that this process can be used to produce very small parts like bolts to very large parts of turbine, ships, shafts, very large tubes. So these are the forged parts. Next process is extrusion. So extrusion is a process where a material undergoes plastic deformation by the application of a force causing that material to flow through the orifice or die. The material adopts the cross-sectional profile of the die. So in this figure we can see the extrusion process. This is the ram, this is the dummy block or pressure plate, there is a billet which is placed inside the cylinder, and this is the die. So whatever the cross section of the die, we will get the cross section as the opening of the die, same as the opening of the die. So we apply pressure through the ram on the pressure plate or dummy block. Dummy block applies pressure to the billet, and through the opening of the die the material extrudes. We can get the extruded product through the opening of the die. So various types of extrusion processes are there. Some of them are shown here, like direct extrusion process and direct extrusion process. The ram direction, ram travel direction and the extruded product direction is same, but the frictional forces are larger in direct extrusion process because whole metallic surface, whole billet surface withstand undergoes and there is a friction on the surface on the whole billet from the die surface and from the cylinder surface. In indirect extrusion process, the extruded metal direction and the ram travel direction is opposite. So in indirect extrusion process, only plastic deformation occurs at the material when there is a contact with the ram, whereas the material which is farther away from the ram do not plastically deform. So the friction is always less in indirect extrusion process. So in hydrostatic extrusion process, we can do the extrusion on the brittle material as well. So in hydrostatic extrusion, there is a ram and it do not apply pressure directly onto the billet. Container is filled with the fluid, the ram applies pressure to the fluid and fluid applies pressure to the billet and extrusion of the material takes place. So through this process, brittle material can also be extruded. So extrusion pressure and ram travel plot is shown here. As we know, the more friction is there in direct extrusion process as compared to indirect extrusion process. So extrusion process, extrusion pressure required is more in direct extrusion process, as we can see by this value. So more extrusion pressure is required to perform direct extrusion process. In indirect extrusion, this pressure is required to plastically deform the material. But as we can see at the point B, when the extrusion pressure further decreases, why it is decreases? Because as the billet start extruding, so it also reduces the friction force due to decrease in the quantity of billet. So extrusion pressure decreases with the extrusion process, whereas in indirect extrusion, the extrusion pressure remains almost constant. But at the end of extrusion process, where most of the material have extruded and only thin disc of the material of the billet remains inside the cylinder, then extrusion pressure again increases, because extrusion press or ram has to force the material, force the remaining thin disc through the to get through the die. So at this time the extrusion process decreases. So it is generally recommended that when the extrusion process is at the end and when only the thin disc is remaining in the cylinder, we generally recommend that it should be removed from the container, and because it is uneconomical to force the material again, to force the thin disc to get through the die hole. So these are the typical extruded products. Various cross section can be obtained through the extrusion process. Long bars, long channels can be obtained through the extrusion process. So these are the typical cross sections that can be obtained from the extrusion process. Some common defects of extrusion are center burst, piping and surface cracking. So center burst are the internal cracks in the extruded material due to the excessive tensile stress at the center, possibly because of high die angle and low extrusion ratio. Piping is defect, it generally occurs at the end of the extrusion process. It is like a sinkhole at the end of billet under the direct extrusion process. Surface cracking is occurs. Surface cracking usually occurs due to high part temperature, due to low extrusion speed and high strain rates. Next process is drawing process. So drawing can be done on a bar or a wire. So drawing is a cold working process in which the workpiece is pulled through a tapered hole in a die to reduce its diameter. So, tensile force is applied and compressive force is applied by the die on the workpiece. So, we pull the material through the exit side of the die to reduce its cross section. So, drawing can be used to produce the bar or wire, and it's also used to produce the tubes using the mandrel. So, if we want to further get back the property of the cold work material, we want to get back the original property of the material after the cold working, we can do the annealing process. So, during annealing process, what happens? In annealing process, we keep the material in the furnace at a high temperature for a certain duration of time, so that 3 stages occurs. Recovery, recrystallization and grain growth are the 3 stages of annealing to revert back the original property of the material. So, this plot is showing with annealing, with this process, annealing process, the tensile strength decreases and ductility increases, and all the properties revert back to their original properties. So, there are 3 stages of annealing of the cold work material. First step is the recovery, second is the recrystallization, and third is the grain growth. So, during recovery, what happens? There is some relief of internal strain energy by dislocation motion, and dislocation density decreases and dislocation assumes low energy configuration. So, what happens during recovery? So, when the dislocation is there, in cold work material there are huge number of dislocations. So, during recovery, with increasing the temperature, dislocation moves on the slip plane. When the opposite side of dislocation come on a common slip plane, they annihilate, means they merge. Dislocation are the half plane. When they merge, when they come across the other half plane of opposite sign, they merge and forms the single atomic plane. So, this process is called the dislocation annihilation. So, during recovery, what happens? Dislocation density decreases due to annihilation of dislocation, and dislocation assumes low energy configuration, and during recrystallization, tensile strength rapidly decreases, a new set of strain free and aqueous grain form that have relatively low dislocation density. So, when the stage changes from recovery to recrystallization, from this figure we can easily see that deformed metal, the deformed worked metal recrystallizes and older grain disappears and newer aqueous grains form during the recrystallization. So, newer grain start forming during the recrystallization process. These are the strain free grains, and the metal becomes softer as the tensile strength decreases, ductility increases, then the metal becomes softer, weaker and more ductile. And after the recrystallization, there is a grain growth. So, during grain growth, what happens? Grain growth is the increase in average grain size of polycrystalline material which proceeds by the grain boundary motion. So, effect of heating during annealing process, there are 3 stages: recovery, recrystallization and grain growth. And with increasing the temperature, what happens to the property? Internal strain decreases during the recovery and recrystallization stages. Strength decreases during all 3 processes. Ductility increases during the recrystallization, and after the recrystallization, if we further increase the temperature of the material, grain size increases and grain growth is there, which further decrease the strength. So thank you for watching the video. If you have any query, you can ask in the chat box. Some comments are there. What could be the best technique for removing oxide scale and from the hot work material before forging? So during the forging, oxide scales, as we have seen in the this video, you can see the oxide scale and the surface oxide layer present on the surface removes, but what happens, it do not remove completely, so it always remain on the surface of the material. Some oxide oxide and the scales are always present on the hot work material. This process is also called the upsetting operation. So no other caution is there. Thank you for watching the video.